How do I know this is implicit differentiation? Yeah, there's y's all over the place in there. It's not solved for y. It can't really be solved for y. I'm not sure how you would even go about doing that. So we certainly have to do implicit differentiation. And what do you notice about both the left side of the equation and the right side of the equation? This is important. Yeah, Mason. Yeah, we got a couple of product rules going on in here. Very good. If you don't recognize those things right off the bat, you're out of luck. Like, you're not getting any further with a question like this if you don't recognize that it's implicit differentiation and there's product rule and that kind of stuff going on. So the derivative of the first thing is pretty straightforward. 2x times the second thing, cos cubed y plus the first thing times the derivative of the second thing. What's left? So remember, there's the three parts, three stages of taking a derivative like this, of something like this, cos cubed y. The exponent, take 3 out front, now it's cos squared y. The rest of that doesn't change, like it's just y, nothing else changes. It doesn't change the sign. I'm just handling the exponent here, not changing anything else. Then the cos part, derivative of cos is negative sine, so negative sine y. There's no exponent there. I've seen that on some learning goals, that people are keeping the exponent there, no exponent there, right? What was the tip that we talked about yesterday? Think about it like this. Cos y all cubed. So when I get that, if I take the derivative of that, let's do it like this. I get 3 cos y squared, and then the derivative of what's inside. So notice, what's inside the brackets has no exponent, right? So it's just negative sine y. Whoops, oh dear. Okay, so what's left? Very nice. dy by dx, the derivative of the angle. Okay, and I think that's done for that side of the equation. And then I do the derivative of the other side. And then a big part of these questions is isolating for dy by dx. So if I take my two dy by dx terms to one side, 2x cos cubed y plus sine x sine y equals cos x cos y dy by dx. And so this has a negative in it. Be careful. There's so many little things going on. This has a negative in it. So it's like negative x squared. So when I take it to the other side, it's going to be positive. So plus. So I did the sides this way so that everything was nice and positive. Okay, and then 3x squared. I'm going to clean this up a little bit. 3x squared cos squared y sine y dy by dx. Okay, factor. I think we got it. Again, knowing the steps, what you're supposed to do, pretty straightforward. I think most people are probably okay with that. It's just the mess of taking that derivative and all the little product rules and dy by dx's and that kind of thing and just working out the algebra. That's the hard part. Remember what we said at the very beginning of this course? That a lot of the ideas are pretty simple and straightforward. I mean, some of the stuff we're doing is from grade 9, right? Finding equations of lines, but it's the algebra that's so much more challenging than what we've done in the past. Everybody okay? All right. Here we go. What's different about this one? Yep. What else? Yeah, good. Everybody hates that domain. It's not from 0 to 2 pi like we're familiar with and like we like, or from 0 to pi. It's from negative pi to pi. So rotating backwards from where the terminal arm starts and angles in standard position. Makes it a little bit messier. But anyway, this is the kind of thing that we can practice and get a bit better at. So if I'm finding critical value, now again, there's different levels to how you approach a question like this mentally. This is the one where on the test earlier, a lot of people got stuck and just didn't know what it was asking. You probably knew how to do it. You probably have the skills to do it, but didn't quite understand what it was asking. Find the critical values, intervals of increase and decrease, and local extrema for this. What is it actually asking me to do? Like, what are the steps of what I need to do to solve this question? Yellow? Yeah, first derivative. Do I have to go any further? Yeah, do stuff with the first derivative, but I don't need the second derivative, right? Like this is asking me to do a bunch of work with the first derivative, so we're going to do that and do a first derivative chart, basically, to find the intervals of increase and the critical values. When it says find the critical values, I said this yesterday, but it means find the points, right? So you got to find the y values as well, which is kind of part of our process, so most people are okay with that, but derivative of sine x. Now these are being added, so there's no product rule here. It's just cos x. And the derivative of cos x is negative sine x. These ones are really interesting because if I took the second derivative and then the third derivative and then the fourth derivative, you kind of could see that there's like a pattern of what happens. It just kind of like flips back and forth between a few different ones, right? It would just sort of rotate, and eventually it would be, I think, the original function again, sine x plus cos x. It's kind of interesting. Okay, so I want to know, this is one, we saw this in MHF one day, I remember. We're going to say y prime exists for all x. We just always make that statement. So where is y prime equal to 0? Couple of different ways to solve this. You could just think, I'm going to do this first. Like this is something that I know. I know where cos x and sine x are the same. From special triangles, I know the answer to that. But there's another nice algebraic way of solving this. If I divide both sides by cos of x. Because if all I do is say, I know where they're equal. That's like by inspection, which is fine. But if we want to do it where in like an algebraic way showing our work, then this is how we would do it. So cos x over cos x is 1. Sine x over cos x is tan. So now I can solve like where is tan x equal to 1. Now I have something that I can solve a little bit better. And where is tan x equal to 1? Nice. If I think about my special triangles, 1, 1, and root 2, tan is opposite over adjacent, so it's the one that doesn't worry about the hypotenuse, so it's 1 over 1, so it's 1. And this is also the one where cos and sine are the same. They're both 1 over root 2. right? So all of that fits. It's all the same thing. And, this is tricky. If the related angle is pi by 4 in our domain, what's x? So I'm rotating this way and rotating this way. And I want to know, where is tan positive? Just in general in the first and third quadrants, right? So how do I get to the first and third quadrants given what I've done so far? Well, the first quadrant is easy. That's just pi over 4. How do I get to the third quadrant? Because I don't rotate. Look, this is negative pi here. So I can't rotate around this way to get into the third quadrant. How do I get to the third quadrant? By going this direction. How much in this direction do we have to rotate to get to the third quadrant? Negative pi would take me all the way to here, right? So if I consider my related angle, I don't quite go all the way. How far do I actually go? Not 7 pi by 4. That would take me all the way around like this, or all the way around like this to the positive one. It would take me to the positive one. Very nice. So 3 pi by 4 will take me into this quadrant if I rotate this way, and we say negative so that it rotates this direction. That's a tricky thing. In MHF, that's something some people never get. And I think my guess is they probably kind of give up. They're like, nah, what's there going to be one question on the test? I'll just not get that one right. Some people make that. I'll work on something else. I got biology too, I'll do that. Right? Some people make that investment. Hey, we all do. But negative 3 pi by 4. It's something that now I think we can get a hang of this when we revisit it the second time around. Think about it. Think about the domain negative pi, which would be starting at your terminal arm, rotating the other direction, and positive pi, rotating the regular direction. And just think about like how far you rotate, that kind of thing. And it's still the same. Which quadrant? I'm trying to get into quadrant 3 because that's where tan is positive. Like that part's still the same. All right. Now what are we going to do? Our chart. So I start at the beginning of the interval of the domain, negative pi less than x less than the next value that's going to show up, which is going to be that one we just talked about, negative 3 pi over 4. And then negative 3 pi over 4 less than pi over 4. Less than or equal to, I missed that in the first one, less than or equal to pi. Oh, not f. Y prime and y. So this one kind of works out nicely because I can use negative pi for this domain. The question we looked at from yesterday that we looked at really quickly at the beginning of class today, if the beginning of my domain was one of the solutions, remember how that came up? Then I can't do this because its value is going to be 0. It was a local minimum in that example we were looking at. But in this case, it's not. It's just part of that interval. So I can use negative pi. So I don't have to worry about figuring out another value. But if you want to figure out another value, you can do that too. Okay, and I think this one works out to be negative. And then I get 0. And then I can use 0 for this one. And this is one where like, hey, folks, the derivative is actually pretty easy. It might be faster to just work it out in your head than do it on your calculator. Like the cosine of 0 minus the sine of 0, that's something that we should be able to work out pretty easily. Cosine of 0 is 1, sine of 0 is 0, so 1 minus 0 is 1, so this is positive. And then here it's going to be 0. And then again, pi, the cos of pi is -1. The sine of pi is 0, so -1 minus 0 is negative, so negative, right? Like that's probably faster, especially if you're good at this stuff. So let's see, we have decreasing. This is the first derivative chart. So decreasing, increasing, decreasing. Decreasing to 0 to increasing is a local min. And it occurs at -3 pi over 4 something. Increasing, then 0, then decreasing is a local max. And that occurs at pi over 4, comma something. And here's where we would use the original equation, which was sine x plus cos x. And again, you can punch this into your calculator, but you could also use special triangles to do this one. It's root 2 over 2 plus root 2 over 2, which is just root 2. And it works out that way for both of them, it turns out. And I think we're done. Any questions? Oops. All right, let's move on. So what do I notice about this one? This is it's a different function. It's sine x times cos x. The last one was sine x plus cos x. The domain is different. It's from 0 to 2 pi. That's the one we like, that we're familiar with. And it's asking the same general idea as the last one, except it's asking about the second derivative. Find the points of inflection and intervals of concavity. So the last one was asking, and to me, again, just going back and taking a moment and reflecting on those questions. The first question was asking, what are the intervals of increase and decrease in the critical values? And this one's asking, what are the points of inflection and intervals of concavity? And that just tells me, what does the second derivative give us? What does the first derivative give us, right? That really highlights what each of those things gives us. Something we talked about in the last unit. What does the first derivative tell me? What does the second derivative tell me? What does the chart give me? That kind of thing. All right, so y prime. Go ahead and beat me to this. What do I notice when I start taking the derivative of this one? Product rule, product rule, product rule. Sine x times cos x makes it a little bit trickier. So derivative of the first thing is cos x times the second thing, which is cos x, plus the first thing times the derivative of the second thing. Look at this. Cos squared x minus sine squared x. A lot of these work out nicely. They kind of have these nice little patterns. Okay, and we're doing concavity, so we need the second derivative, and now I don't have product rule. Is that right? -4 sine x cos x? Interesting. It's just very similar to the derivative that or the function that we started with. So many of these little things that pop up doing this. Okay, so what do I want to do next? Y double prime exists for all x. And where is it equal to 0? What do I do to solve this one? Start by dividing both sides by -4. Sine x times cos x is 0. What do I say? I wonder if people are like I know this stuff is tricky. There's all different ones. We haven't practiced this in a while, but like, are people hesitant? Like, don't be hesitant to try. Like, think about what it is. I don't know if this one's too easy or if we're like feeling, gosh, this stuff is really hard. I'd rather you just do it, Mr. Miller. Just tell us what to do. No. What do we do? Yeah, isn't this one already kind of set up to just solve? Like, I hope people were thinking that. So that means sine x equals 0 or cos x equals 0. If we didn't notice that, again, you really have to start pushing yourself to try to think about what you need to do to solve these trig functions. You're trying to get something times something. Whether we split it into some kind of trinomial using identities and factor to get it something times something, or whether we common factor to get it something times something, or whether it's already in that form, we're trying to get something times something, so either of those somethings can be 0. Now I'm going to consider my domain 0 to 2 pi. So that means x is going to be what? Yellow. Nice. How'd you get that? Thinking about the graph. You kind of, if you've done this enough times, you're kind of starting to memorize these things, aren't you? You kind of just know, like, oh yeah, this one I know it's this. And then what about over here? Somebody else? Thank you. And all those are in our domain? Like, that was the point, but we tried to consider that when we did this. All right. So starting at 0. And 0 is one of those points, so watch how I do this differently from how I did the last one. It's not, I don't include it in an interval. It's a point of inflection. It's its own row in the table. And I got to do these in order. And I'm going to have a lot of them. All right, so this is 0, this is 0, this is 0, this is 0, this is 0. Hey, this is kind of a nice little trick. Here's sine. Ugh, that was terrible. Here's a better sine. Nope, still terrible. Let's see. Better. That's sine. Cosine. Like, kind of like that. Yep, that's good enough. So then I can think about it like this, can't I? In that interval from 0 to pi by 2, sine and cosine are both positive. When I plug them in and multiply by -4, I'm going to get negative. See how big picture, like trigonometry is so big picture. There's so many different ways of solving it. Sure, I could punch it into my calculator. Sure, I could think about a value in that interval, pi by 3, pi by 4, like there's lots of different ones in there between 0 and pi by 2. But I could also think about the graph. In that interval, what's happening for sine and cosine, okay? And I can use a graph for all of them, and it flips back and forth. I'm not just taking that for granted. I am calculating that just to be sure. So this is concave down, concave up, concave down, concave up. So if it's changing from concave down to concave up, this is a point of inflection. Changing from concave up to concave down, that's what a point of inflection is. Just to save time, I'm going to fill in some of these gaps. Again, turns out it's actually pretty easy. Evaluating the original function, which was sine x times cos x at pi by 2, ends up being like 0 times 1, so it's just 0 and 0 and 0. They all work out to 0. And then here's my question, what's happening here? We don't know, because we don't know what happened before. We can guess, but we don't actually know what's happening there, okay? So we just leave it. We don't. Just leave it blank. Any questions? Yes?
On the previous one, you showed us, you said that you put a horizontal tangent line on that line.
Yep. Yep.
So how come we don't get the same person?
Well, do we know what's happening here? Because it's the second derivative, not the first derivative. So you can put horizontal tangent line because we know at least that. If you're sketching, I think that's important to think about because that's going to change what your sketch looks like. So if I was sketching this, this is kind of a tangent. If I was sketching this, if I know it's a horizontal tangent line, then I'm going to come down and I'm going to make it look like that, like it's doing that. And if it's not, then I'm going to just maybe go like that. You know what I mean? So if your sketch is going to change the look of your sketch a little bit. So for the first derivative chart, it's maybe important to say, hey, this is a horizontal tangent line. For this one, second derivative, I don't think it is useful to speculate or worry about what's happening. Does that make sense? Okay. Awesome. All right, one more. We got 12 minutes. I think we can do it. I know we're kind of flying here, but let's try to do a sketch. Oh, and this one's neat. It's got something, kind of interesting going on, so I think it's important to try it. So when you're doing your practice later, you don't wonder. When you're doing a sketch, we go back to when we were sketching previously, and I think to myself, like, remember what we do to sketch. We find the intercepts. We find the asymptotes. We find that we go through all those steps. So it's the same thing here. The exact order in which you do them is kind of up to you. So I'm going to start this time by, I don't know why I'm going to do this, but I'm going to take both derivatives. So this one's interesting because it's got an x all by itself, x minus 2 sine x. So the derivative of x is 1, and the derivative of negative 2 sine x is just negative 2 cos x. And then if I take the second derivative, the 1 is gone, And the derivative of cos is negative sine, so it's going to be positive 2 sine x. Not often that the derivative ends up being like, or at least not in our experience from previous unit, where the derivative is actually more simple than the original function, right? But sometimes this is what happens in trig, and we kind of set up these questions this way because it makes it easier to examine the properties and the stuff that's happening. All right, so here's what I'm going to do now. I'm going to find the y-intercept. How do I find a y-intercept? That just occurs when x is 0. So 0 minus 2 times the sine of 0. And what is that? Zero. And now I'm going to find the x-intercepts. And here's where we run into a bit of a problem. What do you think about this? When is that function equal to 0? When negative 2 times the sine of an angle is equal to the angle. Like if I tried to solve this, I'd get 0 equals x minus 2 sine x. Have we ever solved anything like that? I don't think so. We don't know how to do this. It's an interesting little thing, I think. When is x equal to 2 times the sine? So when is the angle equal to 2 times the sine of itself? But that's not really something we know how to solve. So I know one of the intercepts, because if the y-intercept is 0, there's an x-intercept 0. But this is too hard. So that's going to happen sometimes when you've got an x and a sine or a cosine of x or something like that. You know, when you have an x outside, that's not something we've ever explored solving. Okay. So, let's see. Asymptotes. Whoops. None. But we're just going to consider it because that's part of curve sketching, is if there were asymptotes, we need to think about that. If there was a tan or something in here, we would need to certainly do that. So now I'm going to look for the critical values. I don't have to do a first derivative chart, but I do have to consider the critical values. Critical values occur when the first derivative is 0, or when it does not exist, but it exists everywhere. So that's when, whoops, this is second derivative. That's when 1 minus 2 cos x is equal to 0. So that's when cos x equals 1/2. Okay, you can fill in those parts. Hopefully that's one that we know. And again, it's 0 to 2 pi. Yeah. I think it's positive. I move the negative 2 cos x over, and it becomes positive, then I divide by 2. Okay, and then points of inflection occur when double prime is equal to 0, and that was 2 sine x equals 0. We've already done this one today, 0, pi, and 2 pi. All right, our chart. Again, 0 is the beginning of the domain that we're graphing on, but it was also one of the points of inflection that we just found, so I include it there. And then from 0 less than x, not less than or equal to, less than pi, and then pi. Okay, so it's 0, 0, 0. Between 0 and pi, I got a nice value that I could use, which would be pi over 2. Sub that in to the second derivative, which was 2 sine x. And I'm going to get positive here. And then sub in 3 pi by 2, and I'm going to get negative here. So this is concave up, concave down. And I need to know my start points and my end points. This is the start, and it's 0, 0. This is a point of inflection at pi something, and this is the end at 2 pi, and I think it's, oh, this is interesting. The function is x minus 2 sine x. So if x is 2 pi, the sine of 2 pi is 0, so times 2 is 0, so it's x, which is 2 pi minus 0, so it's 2 pi. It's got this really interesting, like if we continued on, you're going to get a lot of these points, and this one is pi pi, 2 pi, 2 pi. And that's going to continue all the way along this curve. It's an interesting curve, this one. I need a couple more things. I look back at my points, sorry, my critical values. Pi by 3 is in here, where it's concave up. Okay, so that's a local min. So pi by 3, and it works out to negative 0.68. So it's a local min because it's concave up, and the other one is a local max because in the concave down interval. The other one was 5 pi by 3. And I'm plugging these into my calculator to check them. We're just kind of doing it quickly. And this one goes to 7.0. That is rounded, but it's like it's big. Oh, we only have 2 minutes. A, B, C, D, E. All right. Putting all the pieces together. This is tricky. Every sketch is a little bit different. Sometimes I want my graph to count by ones, 1, 2, 3, 4. Sometimes that's the best way to do it because that's how my values kind of are. In this case, I think I can go pi by 3. So pi by 3, 2 pi by 3, 3 pi by 3, 4 pi by 3, 5 pi by 3, 6 pi by 3, 2 pi. And there's our full sketch. So pi by 3 and negative 6.68 is a local min, so that occurs there. Turns out there's an X-intercept at about 1.9. Remember, we couldn't calculate that, but I calculated it earlier with technology. And we've got our point at 0, 0. I have a point of inflection at pi and pi. That's point C. This is point A. This is point B. We didn't have that one listed. I have a local max at 5 pi by 3, so that's right around here. That's D. And then the end point is E is 2 pi and 2 pi. It's right about there. So this curve looks something like this. Point of inflection, local max, end. Oh my gosh, we did it. Any questions? Kind of fit it in. I know it's a bit rushed, but all that work that I had done previously, finding all those values, like that's not trivial stuff. Getting those right by punching them into your calculator is something you really need to do, go over yourself and practice. So make sure that you take the time.